Alright, so we're going to learn about taking the second derivative and doing a number line analysis a little bit more. I do apologize for the noise. They're doing construction, kind of repaving outside of my street, and they're going to be doing it all day, so we're just going to have to deal with it, and hopefully the video turns out okay. So we have a graph, and in this case, we already have g prime of x, and we want to determine the intervals where g of x is concave up, is concave down, and any points of inflection. So just like I said last time we did these with increasing, decreasing, anytime we see words like increasing, decreasing, max, min, and critical point, those words we're always thinking that we're going to take the first derivative and we're going to set it equal to 0 or dne, now that we know about the dne case. Whenever we see the words concave up, concave down, or inflection point, then we're going to do the same process, but we're going to take the second derivative and set the second derivative equal to 0 or dne. So that's just kind of something to remember, be on the lookout for. So we see that second case, so we need to take the second derivative. We're starting with the first derivative, so in this case we only need to do the derivative of that once. So g double prime of x, this is a fraction, so we're going to have to do quotient rule. So low, and low is going to be x to the fourth plus 6x squared plus 9 times d high, the derivative of negative 12x is negative 12, minus high, d low, 4x cubed plus 12x, all over low squared. So this one is a little bit complicated, but we'll just go at it. So we're gonna distribute on the exam. You really wouldn't get anything this complicated on the exam, but I want to show something a little more complicated just so if we see that, we kind of understand a lot of the processes. So we're gonna get in the numerator negative 12x to the fourth. Negative 12 times 6 is negative 72, x to the second, and then I always do these like 9 times 11 is 99 and then add one more. So 99 plus 9 is 108 to get to multiplying by 12. So minus 108. And then here this negative also needs to distribute. So if I distribute it now, that'll turn positive. You can distribute it to one or the other. So this will be plus, I'm going to do the 12x times 4 is 48, and then it'll be x to the fourth. And then 12 times 12 is plus 144 x squared. Now in the denominator, I'm going to do something a little bit fancy. And I'm actually going to factor it. And so we're going to factor kind of the inside. You can do the x method or however you do it, but this ends up being x plus 3 times x plus 3 or x plus 3 squared. So we have x plus 3 squared, but then, sorry, x squared plus 3 squared. And then another squared. The reason it's x squared is because if we had x squared plus 6x plus 9, that would be x plus 3 and x plus 3. But whenever you have, say, like x to the fourth plus 6x squared plus 9, if this is doubled, right, this is like to the first power, it's doubled, it's always the same as the x method, but just instead of using x to the first, now we're using x squared. So it's x squared plus 3 and x squared plus 3. Or we can just write this as x squared plus 3 squared. So that's what I did over there. So next, in the numerator, we're going to combine like terms. So anything that has an x to the fourth term, I'm going to underline once. X squared term gets 2 underlines. And the number will get 3 underlines. So this gives us 36 x to the fourth, then 144 minus 72 is plus 72, x squared, and then minus 108, all divided by x squared plus 3, and actually when we square it, it'll become to the fourth power. Now we can factor out a 36, and we get x to the fourth plus 2x squared minus 3, and this will be something that we can again factor out pretty easily. Okay, and so we're going to do that same x method with the fourth power. And so we have 36, and we'll end up with x squared plus 3 and x squared minus 1. Right, the plus 3 and minus 1 gives us 2, and we have x squared because it was x squared and x to the fourth, not x squared and x, divided by x squared plus 3 to the fourth. Now, in general, normally, you would say, hey, let's cancel out an x squared plus 3, and you would keep going. But with number line analysis, I don't cancel anything with an x out ever, because when you cancel it out, it actually removes it from us. So when you cancel it out, basically, you're no longer analyzing it, but when you cancel it out, it would have been a whole, it would have been DNE, so you do have to analyze it. So we're just going to stop here. So what we're going to do at this step is we're going to set it equal to 0 and DNE, both of them. So when we set it equal to 0, we're going to set the top to 0. So 36 times x squared plus 3 times x squared minus 1 equals to 0. So we have x squared plus 3 could be 0, or we have x squared minus 1 could be 0, right? We divide by the 36. This gives us x squared equals negative 3. When we square root that, this is no solution. So that part never actually materializes. On this side, you can either factor it and do like an x plus 1 and an x minus 1, and so you'll get x equals 1 and negative 1. Or you can add, that's one way to look at it. The other way you can look at it is you could add 1 to both sides and take the square root of it. And just remember, the square root when we're dealing with x's gives plus or minus 1. So both ways we'll get plus or minus 1. So that's the 0 case. The DNE case is we're going to take x squared plus 3, the bottom, to the fourth power. Set that equal to 0. Take the fourth root of both sides. X squared plus 3 equals 0. You'll see this is the same that we had over there. X squared equals negative 3. You can't square root a negative number, so we get no solution again. Now, 1 and negative 1, I want to talk about these very quickly. These are not inflection points yet. They're only inflection points if they change concavity. So we have to do the number line analysis. So what I like to kind of write here when I'm doing these is that these are I write them as, I just write PIP. Pips, they're possible inflection points. So again, possible inflection points. We have to see, does the concavity change signs to determine if they actually are. So I'm going to make a number line up here, and it's very, very important that we label this as G double prime, right? Because we could have also had a number line for G prime. We need to label this one G double prime. So we're going to have negative 1, and we're going to have positive 1. So I need to plug in a number smaller than negative 1, and we're going to plug it in to where we had it kind of most factored, which was over here. So let's say negative 2. If I plug in negative 2, now when we square negative 2, it's going to become positive, and then when we add 3, this part's always going to be positive no matter what. Same thing with this denominator. X squared is positive, plus 3 is positive, and to the fourth power, this part's always going to be positive no matter what. 36 is obviously always positive. So really the only place where we have to actually think about is this guy right here. So if I take negative 2 and I square it, I get 4, and 4 minus 1 is positive. So this is everything's positive. I'm going to put a plus there. Then if I do, like, say 0, right? 0's in between negative 1 and 1. That's an easy thing to plug in. Again, everything was always positive, but in this x squared minus 1 case, 0 squared minus 1 gives a negative. And then if I plug in 2, 2 squared is 4 again. 4 minus 1 gives a positive. And so what I like to do on this number line analysis is I just kind of draw it in as concave up, concave down, concave up. So we would say g of x is concave up from negative infinity to negative 1, union 1 to infinity, because g double prime of x is positive or is greater than 0 for those intervals. Similarly, we'll do the same thing with concave down. G of x is concave down for negative 1 to 1, because g double prime of x this time is less than 0 for that interval. And then our inflection points are based on, did it change concavity? So did it switch between concave up and concave down? Well, in both of these cases they did. So x equals -1 and x equals 1 are inflection points. Because, now you can either say g double prime of x changes signs, or you can say g of x changes concavity. Either way works. I'm going to use because g double prime of x changes signs. At, x equals 1 and -1. But you could have also said because g of x changes concavity. So this, this is kind of what we need to practice, make sure we're writing correctly. And just kind of going back up to yesterday's work, we saw up here -2 when we had this -2. It didn't change sign, so -2 was not an inflection point. Whereas for our values today, -1 and 1, they did change signs. Now, I know this was complicated with the quotient rule. Most of the time, you're not going to have something like that. That's very, very rare. I just wanted to show it so we could see something, extremely difficult. Now, there is one more test. This is a very rare test. I almost never use this test. It's something we'll learn about right now. And the only time I ever use this test is if the AP test literally asks me to use the second derivative test, or there's a very kind of rare situation where you might be given the second derivative and not the first derivative. So in that case, then we might need to use the second derivative test. But what the second derivative test is it's actually an alternate way to find relative maximums and minimums. But you use the second derivative instead. So what's the way that we kind of know and that we use most of the time? What we know is we take the first derivative, set it to 0, and now we can also set it to d and e, right? Set the top to 0, the bottom to 0. We get our critical points. We make a number line analysis, right? And then we basically say where does, if f prime goes from positive to negative, then that's a max. And if it goes from negative to positive, then that's a minimum. So that's the way that we know already. This is a different way to do it. And so in this way, what we kind of say is, if we know some value, say like x equals a, is a critical point. Okay. So if we know that it's a critical point, then what we kind of know is we know that either f prime of x equals 0 or d and e, right? Like basically f prime of x was 0 or it was d and e. And this is a critical point. Now, it's a possible inflection point. It's a possible inflection point. So there are kind of three cases. So case 1, case 2, and case 3. And they're all based on the second derivative. So if f double prime at a, if we plug in a, if the second derivative is positive, what that means is that it's concave up there. What would concave up look like? Concave up would look like that. And if it's a critical point, it'd be that bottom point. Right, how do I know it's that bottom point? Because that's where f prime of x would be 0. That would make it a critical point. So if f double prime is greater than 0, then what we know is this is a minimum. You can just see it from that picture. So we have a minimum. So I'm going to move the picture over. It's still important to draw. So we'll say if f double prime of a is greater than 0, then x equals a is a relative minimum. And you can just kind of see that from the picture that we drew. Then we'll also have the opposite case. If f double prime is less than 0, when we plug in a, right, that's concave down. What does concave down look like? It's this shape. And we know it's that top point because, again, f prime of x was equal to 0. So that's showing a relative maximum. So then x equals a is a relative maximum. And then basically our third case would be being neither positive or negative, which would be being 0. So our third case would be if we get 0. So if f double prime of a equals 0, right? Well, when it's equal to 0, what happens is this is where we have one of those vertical tangents, right? We might have had, concave. Oops, I drew that backwards. Oh, yeah. So we might have had, we can do it this way, it's a little easier. Concave up, and then it gets this vertical tangent, and now it's concave down. So we might have that point right there, and this would be basically a vertical tangent. And so then x equals a is neither. Now, if you get D and E, that's different. If you get D and E, it's just kind of like we don't know, because you could have something like this, right? And that is a minimum. Or you could have something, a cusp, and that's a maximum. So D and E, we don't really know. So if you want to kind of add yourself like a little case, like, if f double prime of a is D and E or undefined, then it's just kind of like we don't know. So in that case, the second derivative test fails, and you would just have to go back to this process of doing the number line analysis. And honestly, I never do the second derivative test unless I have to. I do this process 99% of the time. But I do want to practice it. It is important just to see it in action and to be able to do it just in case we do have to do it. And some people like this way better. So to use the second derivative test, first we take the first derivative. F prime of x equals 4x cubed minus 12x squared. We're still going to set it equal to 0. We don't have to do the D and E because there's no fraction. And factor out of 4x squared. We get x minus 3. And so we have x equals 0 and 3. These are our critical points. Now, the way that we would normally do this is we would make a number line. We would make it for f prime. We would do 0, and we would do 3. But we're not going to do this because it asked us to use the second derivative test. So using the second derivative test, what we do is we then take the second derivative, right? So I'm going to go back up to our first line and take the derivative of this guy. So the derivative is going to give us 12x squared minus 24x. And now we're going to plug in 0. And we got 0. And then we'll also plug in 3. And that gives us 12 times 9. And then minus 24 times 3. And it doesn't even matter if it's what number it is. It just actually matters if it's greater than 0 or less than 0. But if you want to actually plug it in, you can. And so 12 times 9 is 108. And then minus 24 times 3 is 72. And so I don't care what the number is, I just care that it's greater than 0. And so what we would say is x equals 0 is neither a relative max or min, because f double prime of 0 equals 0. And we could say x equals 3 is, and remember, if you forget, well, what does greater than 0 mean on double prime? Greater than 0 means it's concave up. So if you forget, just draw a little concave up, and oh yeah, that's a minimum because it's at the bottom. So x equals 3 is a relative minimum because f double prime of 3 was greater than 0. So that's kind of the explanation using the second derivative test. And you'll get just as many points for this as if you had done it our old way. Now, just to kind of show the old way one more time and just kind of check our work, we're not going to do this every time, but we'll do it once to check our work and remember what the old way looked like. The old way was, we're going to do a number line. We need to make sure we label it f prime. That's very important because we could also label it f double prime, and that would be for concavity. So we're going to label it f prime. We're going to plug in 0, we're going to plug in 3, and we're going to plug these into f prime. Now actually I don't plug it into that line, I usually plug it into my most factored line. So if I take a -1, when I square it, it's positive, and actually anything squared is always going to be positive. And -1 minus 3 is negative. So that's negative. If I plug in 1, 1 squared, again, always positive. 1 minus 3 is negative again. If I take 4, 4 squared is positive. 4 minus 3 is also positive. So we had decreasing, decreasing, increasing. In the old way, we would have seen, yes, x equals 0 is neither. Our explanation would have been different. Our explanation would have said, because f prime didn't change signs. And then x equals 3 is a minimum. And again, our explanation would have been because f prime changes from negative to positive. So it's a different explanation, a little bit different way of doing it, but we get the same result. Okay, next one has to do with trig, which obviously can be a little bit tougher, but it's something we need to practice. So f prime of theta equals the derivative cosine is negative sine. The 2 is a coefficient, so it's just going to stay. So -2 sine theta. And then we don't need to do the whole d theta dt because this isn't a rate, right? We're taking the derivative with respect to theta in this case. And then the derivative of theta would be -1. So we're going to set this equal to 0. Add 1 to both sides. Divide by -2. And we get -1/2. And so what we need to kind of do is remember our chart, remember our number line. Where does sine of theta equal 1/2? Right, so if you kind of remember the whole sine, cosine, tangent chart. Right, we had 0, and then we had 1/2. And then I'm not going to keep drawing. This was at pi over 6. So we know our answer is going to be some kind of multiple of pi over 6 because it's negative. That's in these two quadrants. So this quadrant is 1 more than the denominator. So 7 pi over 6. And this quadrant is 1 less than double. So 11 pi over 6. So that's kind of how we would figure out what theta is. So theta is 7 pi over 6 or 11 pi over 6. If you want to write out any more math, what you could also write out is we did the inverse sine of both sides. Okay. So these are our critical points. Now again, we could do a number line analysis. That's something that we're allowed to do. Or we could do the second derivative test. And the second derivative test means we're going to take the derivative. And so the derivative -2 sine of theta is going to be -2 cosine of theta. Still negative because the derivative sine is just cosine. So the -2 stays. Then the minus to do is just plug in f double prime of 7 pi over 6. -2. Now, I don't even care what answer 7 pi over 6 gives. I just care, is it positive or negative? Right? And in tangent, 7 pi over 6 is in this, third quadrant. Cosine is a negative value. So we're going to get -2 times a negative value that's going to be positive. A negative times a negative gives us a positive value. And then when we plug in 11 pi over 6, we have -2 times cosine of 11 pi over 6, and that's in the fourth quadrant. That's in the C place. And so that's a positive value. So -2 times a positive, negative times a positive will be a negative. So that's kind of how I thought of that. So what we're going to say is that 7 pi over 6 is, now remember, greater than 0, concave up, is a relative minimum because f double prime of 7 pi over 6 was less than 0. Then we'll say 11 pi over 6 is a relative maximum because f double prime of 11 pi over 6 was greater than 0. So if you like this way better, you can absolutely use this way. If you prefer to do the number lines, that's the way I like to do it. I, 99% of the time do it this way. The only time I actually like doing second derivative test better is actually this case, is for trig. With trig, sometimes plugging in, with the number line on trig is kind of weird. So I like to do this way better just for trig, but for everything else, I always do the number line. So for our homework, most of the homework isn't going to be doing that second derivative test, but we do have a couple. But most of it is, you know, looking at concave up and concave down and doing that whole number line analysis for the second derivative, which is kind of what we did here and also what we did yesterday analytically on this question here. Now, like I said, a lot of the times when we're actually doing them, we're not going to have to deal with these fractions, and it's a little bit nicer. So anyways, there's that. Hope this made sense, and I will see you guys in class.